This video is for ELEC 1510 Logic Design. This is Lecture 18 on Moore and Mealy state machines. This information corresponds to textbook section 5.8. So far, in our discussion of state diagrams and state tables and state machines, we've just talked about how to design the state variable outputs, meaning that the only outputs that we would ever have in our circuit so far would just be the states or the state variables. So now we're going to talk about how to design state machines that have different outputs. In the first case, if the circuit outputs depend only on the current state, we would call this implementation a Moore machine. If the circuit outputs depend on both the current state and the inputs, we would call this implementation a Mealy machine. Sometimes you can take a description of a state machine and implement it as either a Moore or a Mealy type state machine. Sometimes it can only be one or the other. So let's demonstrate how the state diagram changes when we include outputs in a Moore machine style. In this state diagram, I want to design a state machine that will detect 1, 0, 1 as a sequence at startup. And after that sequence is detected, we want to output a 1 forever. This could be some kind of startup check, say, for the first time that some computer or machine is turned on. So let's start in state A. Now, as you can see, in state A, I now have A/0. The 0 there is the output. So A is the state slash the output. The output is a 0 when I'm in state A because I haven't yet detected anything. If I detect a 0, I return to state A because I haven't yet detected the 1 at the beginning of the 1, 0, 1 sequence. If I detect a 1, I go to state B and I still output a 0, so that's B/0. Now from state B, if I detect a 1, I'll return to state B because I haven't yet detected 1, 0, but I've still detected a 1 that could be the start of the 1, 0, 1 sequence. If I detect a 0, I'll move to state C. That output is still 0, so it's C/0. From C, if I detect a 0, I go back to A because that means I've detected the sequence 1, 0, 0, which is basically useless as far as the 1, 0, 1 sequence is concerned. I have to start completely over. And then if I detect a 1, I'll move on to the final state, which is D, and now we see that the output is 1, so that's D/1. And then from that state, if I detect either a 0 or a 1, I return to state D and always output a 1. Here we see the state table corresponding to the state diagram from the previous slide. I have the current states of the flip-flops, the input X, which is where I detect the startup sequence 1, 0, 1, the next state, and then I've assigned D flip-flop inputs, which just mirror the next states. I've done the state assignment so that for the state variables S1 and S0, A is going to be equal to 0, 0, B is equal to 0, 1, C is equal to 1, 0, and D is equal to 1, 1. Now for the output F, this is a new column in our state table. We know that the output only depends on the current states and that the output is going to be a 1 whenever we're in state D. So F is always a 0 until I get to state D. So that means that the logical function for F in terms of the current states is S1 and S0. So now when I actually draw this circuit, I'm going to have the whole sequential circuit with the 2 flip-flops and the feedback that creates the inputs to the D flip-flops. So I would have had to derive the D flip-flop equations separately. I'm not doing that here because I've done that in the previous lectures. But basically, as the input to the sequential circuit, I have X. As the output from the sequential circuit, I have the 2 state variables, S1 and S0. And now the actual output that I want is F, where F is S1 and S0. So now I just have an extra output that's formed as a combinational circuit of the two output state variables. Let's modify that design slightly now to turn it into a Mealy machine rather than a Moore machine. Again, this is the type of state machine where the output depends not only on the current states but also on the input as well. So again, we want to detect the sequence 101 at startup. After this sequence is detected, we'll output a 1 if the input is ever a 0. So again, we have basically the same set of states. The difference is that now you can see that the states themselves don't have outputs. So rather than A/0, I just have state A. And now the slashes for the outputs are next to the arrows indicating the inputs. So for A, when I detect a 0, I return to state A and I output a 0. So it's 0/0 next to that arrow. If I detect a 1 at A, I output a 0 and I move to state B. From B, if I detect a 1, I output a 0 and return to state B. If I detect a 0, I output a 0 and move to state C. Now for C, it's the same transitions as it was for the Moore machine version. I just output a 0 in either case. And now for state D, if I detect either a 0 or a 1, I return to state D. But when I detect a 0, I output a 1. And when I detect a 1, I output a 0. So here again is the state table, this time for the Mealy machine version, where we want to output a 1 if the input is 0. I've used the same state assignments as I did for the Moore machine version, which means that if we're in state D and we detect a 0 at the input, we're going to output a 1. That means that there's only 1 in the whole column for the output, which is right here, which is where we're in state D. State D is 1, 1 in terms of the state variables, and our input is a 0. The rest of these rows are 0 for the output column. So now that means that the output F is equal to only one minterm of the current states and the input. F is going to be given by S1 and S0 and X prime. So now it's a combination of the current states and the input. So now when drawing the actual circuit design, we've got our sequential circuit here. That's what includes the D flip-flops and also the combinational circuits that form the inputs to the D flip-flops as combinations of the input X and the state variables S1 and S0. The input to this sequential circuit is X. The outputs are S1 and S0. And now the output F is given by the function S1 and S0 and X prime. So I need to route X prime all the way to the output. Now I'm going to invert it. And then I also need S1 and S0 as inputs to that AND gate. And so now, as you can see, the output F is a combination of the input X and the output variables S1 and S0. One thing that's important to note about Mealy machines as opposed to Moore machines is that the state variables S1 and S0 only ever change when the clock changes, but X can change whenever it wants. So F in a Mealy machine can change whenever it wants. In a Moore machine, where F is just a combination of the state variables, F can only ever change on clock changes.